Good day everyone. Today I'll be explaining AVL trees, which are a type of self-balancing binary search tree. We will start by reviewing what a normal binary search tree is, then understand the problem with it. Finally, see how AVL trees solve that problem using something called rotations. By the end of this video, you should clearly understand what an AVL tree is, why it's used, and how it works internally. Before we talk about AVL trees, let's quickly review binary search trees, or BSTs. In a BST, each node has at most two children. Any value smaller than the node goes to the left, and any value larger goes to the right. This structure allows us to search efficiently because at each step we eliminate half of the tree. Also, an important property is that if we do an in-order traversal, the values come out in a sorted order. Although binary search trees are efficient, they have a serious problem. A BST does not balance itself. If we insert values in a sorted order, such as 10, 20, 30, the tree becomes skewed, meaning it looks like a linked list. When this happens, searching, inserting, or deleting values becomes slow. Instead of big O log of n, the time complexity becomes big O of n. This is the main problem that AVL trees are designed to fix. An AVL tree is a self-balancing binary search tree. This means it follows all the rules of a BST, but it also makes sure the tree stays balanced after every insertion and deletion. The name AVL comes from the inventors Adelson Velsky and Landis. The key rule of an AVL tree is that for every node, the height difference between the left and right subtrees is at most 1. To measure balance, AVL trees use something called the balance factor. The balance factor is calculated as the height of the left subtree minus height of the right subtree. If the balance factor is -1, 0, or +1, the node is balanced. If the balance factor becomes +2 or -2, the node is unbalanced and must be fixed. AVL trees check this balance factor after every insertion. When a node becomes unbalanced, AVL trees fix the problem using rotation. Rotation is a small restructuring of the tree that reduces its height and restores balance. The important thing is that the rotation do not break the binary search tree property. The in-order order of elements stays the same. There are two basic rotations, left rotation and right rotation, and from these we get 4 classes. There are exactly 4 imbalances cases in an AVL tree. They are named based on where the insertion happens relative to the unbalanced node. The cases are left left, right right, left right, and right left. 2 of these cases use a single rotation, and the other 2 requires double rotations. Let's start with the LL case. This happens when a node becomes unbalanced, because a value was inserted into the left subtree of the left child. For example, if we insert 50, 20, and 10, the tree becomes heavy on the left side. To fix this, we perform a right rotation. After the rotation, the tree becomes balanced again, and the middle value becomes the new root. The right-right case is the mirror image of the left-left case. It occurs when a value is inserted into the right subtree of the right value. For example, inserting 50, 70, 80, the tree becomes right-heavy. To fix this imbalance, we perform a left rotation, which restores balance. However, the left-right case is more complex and requires a double rotation. This happens when a node is left-heavy, but the insertion occurs in the right subtree of the left child. This creates a zigzag shape. To fix this, we first rotate the left child to the left, and then rotate the root to the right. After these 2 steps, the tree becomes balanced. The right-left case is the opposite of the left-right case. It happens when a node is right-heavy, and the insertion occurs in the left subtree of the right child. This also performs a zigzag shape. We fix it by first rotating the right child to the right, and then rotating the root to the left. The insertion algorithm of an AVL tree follows 4 main steps. First, we insert the value like a normal binary search tree. Second, we update the height of each node, and as we return from the recursion. Third, we compute the balance factor. Finally, if a node becomes unbalanced, we apply the correct rotation. This process ensures the tree remains balanced at all times. Because AVL trees stay balanced, their height is guaranteed to be logarithmic. This means searching, inserting, and deleting elements all take big O log of n time. This is the main advantage of AVL trees over regular binary search trees. Comparing AVL trees with normal binary search trees, we can see that AVL trees guarantee performance, while binary search trees can degrade to O of n. AVL trees will always remain big O log of n. The trade-off is that AVL trees require extra work in the form of rotation and height tracking. To summarize, AVL trees are self-balancing binary trees that maintain efficiency by keeping their height balanced. They use balance factor and rotation to ensure that operation remains fast. AVL trees are especially useful in systems where search speed is critical. And that's it for today. I thank you all for listening, and I hope to see you guys next time.